Hey y'all, it's Miss Summers with your notes today. Today's objective is I can explain how the sun makes life on Earth possible. So that is what we'll be looking at today. We're going to start at the actual sun itself and then sort of move our way towards Earth and see how these two bodies in space are connected. So before we begin, I just want to go over what's on this this little title slide I made. When I was making this a few years ago, I was like, how many different representations of the sun can I find? And I've just kind of looked around and I found a picture like the actual sun. And then I found all these other cultural representations. So this is Ra from ancient Egypt. This is a Japanese goddess, deity. We have Apollo and Helios. And this is Central or South American. I believe it's Mayan, if I'm not mistaken. And this is a Norse representation, like a Viking type deal. And what all these have in common, even though these are all very different cultures, they all thought the sun was important enough that they needed to have somebody or something to deify it, basically, to make it equivalent to a god or a goddess. All right, and what I want you to think about why they did that, it's because even then, thousands of years ago, I think that all people have realized, the sun is a part of our daily lives. It has some importance to us. If this sun were to go away, it would be very, very bad. So keep that in mind as we go through this little note journey of ours, okay? So everything you need to write will be in yellow. It is bolded and highlighted for you. If you want to go through this video and write everything down first and then go back and listen, you're welcome to do that. Or if you just like to listen and then write everything down later, that is also fine. All right, so it's okay to go back. I do not want you just skipping through writing things down and not listening, though. Please listen to the following presentation. So let's begin with what the sun is. That's the bell. Hopefully you're in class now. The sun is the closest star to Earth. It is approximately 93 million miles away. And we see approximately, because you remember from Kepler's first law, that planets go in ellipses or ovals. Sometimes it's closer, sometimes it's farther away. This goes in that little box in the upper right-hand corner of the sheet. What kind of star is the sun? It is a yellow dwarf star. It's actually not really that big compared to other stars in the universe. It's actually kind of a wimpy little star, but it's still important. It was formed about 4.5 billion years ago. It's about halfway through its life right now. So our next question on our note sheet, what two elements are the sun primarily made of? So this is true not only of the sun, but of most stars. If I look over here on this pie chart, the sun is mainly about 3/4 hydrogen. And then the remaining 1/4, or about 1/4, is helium. Now this is the smallest and the second smallest atoms in the entire universe. These are the building blocks of all the others. So the sun is mostly hydrogen and helium. Now, why that's important, what that relates to, is the purpose or the reason that the sun is useful to us. The sun is a source of all energy. Energy is the ability to do work. So where does this energy come from? Well, it comes from a process called nuclear fusion. So you might see that word nuclear and think, okay, I've heard of nuclear power plants. Those things are related, but it's not quite the same. So based on this picture, you can tell that fusion has something with bringing things together. It's called nuclear fusion because it's bringing small hydrogens. So these are hydrogens right here, little tiny pieces. And because the sun is so big and there's so much heat and there's so much gravity, that these little hydrogens, normally they don't want to be together because they have two pluses, and normally those pluses repel one another. Because there's so much gravity on the sun, it's squishing them together. These two hydrogens end up getting stuck or fused into helium. So now there's two pluses, that's helium. Now, this process creates energy, all right? You might have heard this equation from Einstein, the guy with the weird hair and arguably one of the smarter people in the 20th century. He's got this equation, E is equal to mc squared. The energy of something, the energy of these atoms, is equal to their mass. C stands for the speed of light, which is a crazy big number. So little bits of mass can have a whole lot of energy. This is essentially what happens in nuclear power plants, except it's the opposite, if that makes sense. In nuclear power plants, like down the road, you take really big atoms and split them apart. And that's a process called fission, which we'll get to that in a few units when we talk about energy sources. All right, but back to the sun. When fusion happens, you get helium and a little bit of light and heat. Actually, not a little bit, a lot of it. So let's look at how that energy moves now. All right, so we have this big ball of hydrogen turning into helium and releasing energy. So how does that energy get to us? What is that energy in the form of? So it's in the form of electromagnetic waves, which is just basically a fancy word for light. But not all light is visible. So the three types that get to us from the sun are visible light, infrared, which is down here. It's called infrared because it's below the red part. This is heat. And ultraviolet. Ultra means above. So it's ultraviolet because it's above the violet. This is the stuff that gives you sunburn. This is the stuff we can see, visible light. And this is the stuff that makes the earth warm. So how do these three waves, visible light, heat, and ultraviolet rays, how do they get here? They get here by radiation, which is just a way that energy moves through outer space. It doesn't need a liquid or a solid to move through. So our next question, does all the energy from the sun get absorbed by the Earth's surface? And the answer to that is a big fat no. Not all the energy from the sun is absorbed by the Earth's surface. Some of it is reflected back into space. So here's all the sun's energy. If I notice where some of this is bouncing off of, it bounces off things like clouds and icebergs and glaciers. All of those things, to us, they look white, and they look white because they're reflecting all that light back. So that is why we don't burn to a crisp. So some of this energy that doesn't get reflected back gets filtered. So UVB rays, remember UV, that's the sunburn rays. UVB rays get filtered by the ozone layer, which is in the stratosphere, which is a part of the atmosphere that we're going to talk about when we get to our weather unit. All right, so that's a very important layer because obviously if all that UV rays got to us, we would get sunburnt to a crisp all the time, and that would not be fun because sunburns lead to things like skin cancers. So some of the energy is reflected back, some of the energy is filtered out, but some of it does get to us, and that energy is what we love. So I'm on the back of my sheet now. Why the energy that does reach the surface of Earth is a big deal. Thermal energy, and you just need to write thermal energy, heats up the Earth's surface. It makes it nice and warm. The Earth is far enough away from the sun that liquid water can exist on the surface. We are in what's called the Goldilocks zone. So if you remember from the story of Goldilocks, she broke into somebody's house, which is not very nice, first off, but irrelevant. The first porridge was too hot, the second one was too cold, and the one in between was just right. If we were closer to the sun, it'd be too hot. If it were far away from the sun, we'd be too cold. We're in a good spot. That's what makes our planet really sort of super awesome for life. We can have liquid water. So, the Earth is heating up. All right, we're on a sphere. Does it all heat up equally? And no, of course not. All right, you might be saying, and you might already know, that obviously at the equator, you get more direct sunlight. That's fabulous. That is 100% true. Very good. At the poles, especially if you're tilted away, you get less direct sunlight, which makes it colder. Also true. But even in the same place, so let's say you're here, let's all take like an imaginary field trip down to this beach. All right? If we were to go down to this beach and take our shoes off right here, it would be very, very hot right here. It'd be super, super hot. And your little feet would start to burn. And you'd be like, oh my goodness, oh my goodness, oh my goodness. So to remedy that, instead of putting your shoes back on, because you don't want them to get sandy, you would run down here to the water. Nice and cold. Or nice and cooler. All right? It's not because the sand is getting more sunlight than the water, but because of this thing called differential heating. Water takes a lot of energy to heat up. So water heats up and cools down slowly. Slowly. So it'll get warm, but it takes a long time. And it'll get cold, but it'll take a long time. Land does not have that. Land heats up really, really fast and cools down really, really fast. So near an area where you have large bodies of water like oceans, typically their temperature throughout the year is less. So again, let's imagine it. Let's imagine if we go to the Outer Banks, which is in North Carolina. All right, in the summertime, if you go there, it's like 80-some degrees. It's hot. It's warm. But here in Charlotte or Mooresville, it might be like 90. It's hotter. And in the wintertime, here in Mooresville, it'll be like 20 degrees. By the ocean, it might be 40. This water helps moderate it. Water has a moderating effect. And we can see this in this fancy little graph. We have two cities, San Diego and Dallas, Texas. They're on the same latitude. Look, there's a latitude. So they get the same amount of sunlight. San Diego, the coldest it gets is like upper 50s. And then it gets up to like the 70s in the summer. So 20-degree range. That's pretty comfortable. Here in Dallas, which is not near water, it gets down to like the 40s. And it gets all the way up above the 80s. A much larger range. All right, oceans, coastlines are moderated. Landlocked is more extreme. All right, so it heats us up. It keeps us nice and warm. That's cool. That's great. But more importantly, or maybe just as importantly, the sun makes life possible because it gives life energy. So the sun's energy is used by life at the bottom of the food chain. The things at the bottom of the food chain are called producers. This is a producer, this is a producer, that's a producer, this is a producer. What do they all have in common? There's a couple things you could say, but hopefully you're like, they're all plants. Very good. They're all green. Also very good. Producers usually are. What a producer does, A producer is called that because they make their own food using light through photosynthesis. So if you've taken biology, this is like a no-brainer. If you don't give a plant light, it dies because it doesn't have a way to make food. So producers are going to be things like plants, algae, which is that green stuff that like grows in fish tanks, and certain types of bacteria. Bacteria probably would have been the first producers on Earth. So they take in sunlight, they take in carbon dioxide, they make food, and they also make oxygen, which is really super awesome. Super helpful. So why that affects us? Because you're like, I am not a plant, nor am I an algae. I cannot make my own food by photosynthesis, so why does it matter to me? Because, sweet children, we are other organisms called consumers. We either eat the producers or we eat things that eat the producers. And the energy that the plant obtained from the sun gets passed on throughout each level of the food chain. So here's my little plant getting energy. The cricket gets energy from the plant. The frog gets energy from the cricket. And the bird gets energy from the frog. So it's just a chain. It's like the circle of life. If you've seen The Lion King, either the new one or the old one, they're both pretty good. All right? We're all connected. All right? So even though we can't use the energy directly, we use it indirectly. So what I want you to do now, all right? For this last slide, I'm going to post this link. What would happen if the sun disappeared? It's a Vsauce video. You're going to watch it. But before you do, you're going to answer this question. What do you think would happen if the sun disappeared? How long do you think we would last? I want you to jot down your thoughts, and then you're going to watch the video. I think it's like 9 minutes long-ish. Then you're going to go to the page. There will be a discussion post where you are going to answer the prompt. What did you think would happen, and what would happen? Maybe what was something you learned that you didn't think of. All right, afterwards, you're going to do the discussion, like I said, and then your assignment. If you have any questions, just let me know, and have a great day.